All right, so as we talked about a little bit yesterday, a separable differential equation is just one where you have a function in terms of x and a function in terms of y on the right-hand side after a dy dx. So all you need to do is separate the variables. So in order to do that, first thing for this one is to just distribute that squared to both the x and the y. And then we get the y to the left-hand side by dividing by y squared, and the dx to the right-hand side by multiplying by dx. You integrate both sides. Integral of y to the -2 is -1 over y, and that becomes x cubed over 3 plus a constant. And we talked yesterday, yes, both sides get a constant, but we only really need to solve for a singular constant, so we just subtract the constant on the left over to the right-hand side, giving us some other constant on the right. And then my recommendation for separable differential equations when you're looking for the constant value is always, as soon as you've integrated, plug in your initial condition. Some people teach, solve for y first and then find the constant, but that requires you to do a lot of manipulations with a c over here rather than just a number over there. It's your choice. If you want to do it at the end, that's fine. But I've always thought that it's easier to do it right away, and that's what I've always taught. So let's do that. We'll plug in 1 for y. -1 over 1 is -1, and that gives us a 1/3 plus a c over here, which gives us c is equal to -4/3. So we then end up with -1 over y equals x cubed over 3 minus 4/3, or -1 over y equals x cubed minus 4 over 3. And we'll take the reciprocal to get -y equals 3 over x cubed minus 4. And we will divide by the negative to get 3 equals, put a negative out in front, or I prefer to distribute it through there normally, 3 over 4 minus x cubed. And same stuff still applies about looking for the continuous portion that contains your initial condition. So the only discontinuity that we can get from this is if that denominator equals 0. So we'll figure out when it equals 0. That tells us that x cubed can't be 4, or that x can't be cube root of 4, and x equals 1 falls to the left of the cube root of 4. So we would say that this is valid for -infinity to negative cube root of 4. I'm sorry, not negative cube root of 4. I don't know why I said that. It's positive cube root of 4. Good or no?
Good.
Well, what? Somebody said something else. I didn't hear what you said.
Just more affirmation.
That's what I need, is more affirmation.
Not for you, the problem.
Oh, okay.
Well, wait, sorry. Do we have to solve it for y, or can we just leave it as like 1 over y?
No, you have to solve it for y.
Okay.
You must solve for y. All right, let's do another one. dy over y equals dx over x. When we separate the variables there, giving us natural log absolute value y equals natural log absolute value x plus a constant when we integrate both sides. And then we'll plug in our 2's, and you guys can do that and tell me what the constant is while I take my child's corn dogs out of the oven so I don't have to listen to that continuous beeping. Max, the corn dogs are ready. All right. What do we get for our constant there? We end up here with natural log 2 equals natural log 2 plus c. So constant is
0.
0. Perfect. All right. And so we'll go in natural log absolute value y equals natural log absolute value x. And we just solve that pretty easily. Exponentiate it. Absolute value y equals absolute value of x. And this gives us either the positive or negative when we do this. And And we are obviously going to want the positive version of it because we need it to be true for our initial condition. So this just becomes y equals absolute value of x. And we are looking at only the piece of this which is continuous. And even though this has no discontinuities on it, at some point through here when we integrated, we had something that did have some discontinuities in it, right? Up here, we knew that x couldn't be 0. And since x couldn't be 0, we have to pick the piece that includes 2 and is continuous to the right of 0. So we'll set for 0 to infinity. And if we're talking about just 0 to infinity, we could rewrite this as just y equals x if we wanted to, because we're talking about the positive piece. And if we had an initial condition where it was negative and we're talking about the negative piece, we could rewrite it as y equals negative x. Everybody good there? Makes sense? So make sure that there are no discontinuities from any piece after you've integrated. Everyone's all good there? All right, let's do, we'll do 2 more, I think. So we got dy over y plus 5 equals x plus 2 dx. Everybody good there? Separating variables, giving us natural log absolute value y plus 5 equals x squared over 2 plus 2x plus a constant. Yeah? Good or no? Okay. This gives us natural log 6 equals 0 plus 0 plus c. So our constant is the natural log of 6, giving us natural log absolute value y plus 5 is equal to x squared over 2 plus 2x plus ln 6. Everybody good with that? And once again, we exponentiate, giving us just absolute value y plus 5 equals, and then for this part, e to the x squared over 2 plus 2x plus ln 6, we can use exponent rules and rewrite this as the multiplication times e to the ln 6 so that I can take this constant e to the ln 6 and throw it out in front. Everybody good with separating that using the exponent rules?
Yeah.
Okay. Hold on one second. All right, so now we're going to clear out the absolute value by making this y plus 5 equals plus or minus, and then we'll throw the 6 to the front, e to the x squared over 2 plus 2x. And we will subtract the 5, giving us y equals negative 5 plus or minus 6e to the x squared over 2 plus 2x. And we got to pick the correct one for our initial condition. So we'll just do that right now. If x is 0, e to the 0 is 1 times 6 is 6. So negative 5 plus or minus 6 needs to give us 1. So that should be a plus. Everybody good there?
Yes.
All right, cool. So then we'll look through everywhere along the way, x squared over 2 plus 2x plus ln 6, no discontinuities there or anywhere through with any of the x's. So this is valid for negative infinity to infinity. Everyone good? On the domain interval, then, the interval of validity?
Yeah.
Cool. All right, last one. This one we'll have to use exponent rules right off the bat to write it as e to the x over e to the y. And then we'll separate the variables. E to the y dy equals e to the x dx, giving us very easily e to the y equals e to the x plus a constant when we integrate. And plugging in y equals 2 and x equals 0 tells us our constant is e squared minus 1. Good or no? E to the y equals e to the x plus e squared minus 1. Take our natural log of both sides, and we just get natural log of e to the x plus e squared minus 1. A lot of people screw these up and put absolute values around this because they've gotten so used to absolute values during our integration. Now we're just taking the natural log of this. It doesn't need to be put inside an absolute value. And then just make sure that you look for the discontinuity. So anything inside a natural log has to be positive. Well, e to the x is positive, and e squared is positive, and the minus 1, that's going to subtract a lot less than e squared is. So e squared minus 1 right there, that's always positive. And if I add a positive to that, it's always positive. So this is valid for all real numbers. Good or no?
Yeah, that makes sense.
Cool. All right, that's separable differential equations. We'll talk about the one little application of them when we come back for quarter 4. And well, not one, 2 of them. One is exponential growth and decay. The other is this idea of logistic growth. And then we're going to talk about ways to approximate these solutions to differential equations other than slope fields, which there's just the one other method we're going to use called Euler's method. And that will complete the differential equations unit. We can do all of that in easily the first day back in quarter 4. And then we will cover everything we need to know about series after that. And that is it with this 9 weeks.